All right, let's talk about something that drives so many ESP32 developers nuts. It's powerful and, often totally misunderstood dual-core system. If you've ever found yourself fighting with mysterious bugs or just random crashes, you're going to want to stick around for this.
So let me ask you this. Does this sound familiar? Your project's running great, just humming along for hours, but the second you turn on Wi-Fi or Bluetooth, it all goes sideways. It starts crashing or freezing or just acting weird. Well, you're not alone. And the reason why is probably not what you think.
The root of the problem, it usually starts right up here, in our heads, with our mental model of how this thing works. A lot of us kind of picture the ESP32 as either two completely separate computers just duct taped together, or maybe as one big beefy processor that just happens to have two cores. And here's the thing, both of those ideas are just plain wrong, and they lead to really unstable code.
So it's time to pull back the curtain on this dual-core deception. We're going to toss out those flawed models and build a new one, a correct one, from the ground up, based on how the ESP32 actually works.
And here it is, the big secret. The ESP32 is a true Symmetric Multiprocessing system. We just call it SMP for short. Now, this is not just some fancy acronym to throw around. It's the core design principle that changes absolutely everything about how your code runs, how it handles a heavy load, and where all those sneaky bugs are hiding.
So, if you remember just one thing from this whole explainer, please make it this. One scheduler, two cores. That's it. That's the correct mental model that's going to make everything else just click into place. Let's make that our North Star as we go forward.
Okay, so what is symmetric multiprocessing, really? Well, it just means you've got one single operating system, in this case FreeRTOS, with one global scheduler. Think of the scheduler as the project manager for all of your tasks. It looks at the two cores as identical, totally interchangeable workers. There aren't two different managers for two different teams. It's just one boss for the whole operation.
And this visual just lays it out perfectly. See, all of your tasks, doesn't matter if they're high priority, low priority, they all go into one shared pool of work. The FreeRTOS scheduler then looks at this list and basically asks two questions. Who's the most important task that's ready to run right now, and which of my two workers is free? Then it just hands off that task to either Core 0 or Core 1. The key is the tasks aren't owned by any specific core.
Now, I'm sure you've seen this before, right? Core 0 is the pro CPU for all the protocol stuff like Wi-Fi, and Core 1 is the app CPU for all your application code. But what's so important to understand is that this is just a convention. It's a common practice that Espressif set up. It is not a hardwired rule. As far as the FreeRTOS scheduler is concerned, they're both just employees ready for work.
So this is the point you need to burn into your brain. FreeRTOS sees one central to-do list and two identical workers. Whichever worker finishes their job first gets the next most important thing from the list. Simple as that. But this simple idea has some really surprising consequences.
And that brings us directly to the wildest and most surprising result of SMP, something I like to call wandering tasks. Now, this is not a bug. It's an intended feature that can totally feel like a bug if you're not ready for it. This is where the theory gets real. So imagine you write a simple little worker task. You flash your board, you open up the serial monitor, and you see this in the logs. Worker, running on Core 1. Okay, cool. Makes perfect sense. Your application task is running on the application core. Everything feels right with the world. But then, a split second later, you see this. The exact same task, without you changing a single line of code, is now running on Core 0. It literally just jumped. This is what we call task migration, and it is a perfectly normal, totally expected behavior in an SMP system. Your tasks can, and they absolutely will, wander between cores. So, why is this such a big deal? Well, for starters, it means you have to assume that a task might go to sleep on one core and wake up on a completely different one. It means an interrupt that happens on Core 0 could suddenly wake up your task over on Core 1. And the most important one, any data that's shared between tasks absolutely positively must be protected. If two tasks on two different cores try to write to the same variable at the exact same microsecond, you get a race condition. And that means corrupted data and those random, impossible to debug crashes. Okay, deep breath. So if our tasks are just free roaming all over the place, how on earth do we build stable systems? Well, you don't fight the system. You use the tools it gives you. Let's talk about how to take back control using task penning and some really smart design patterns.
So our number one tool in the toolbox is task pinning. When you use the standard xtaskCreate function, you're basically telling the scheduler, hey, I don't really care where this runs, just get it done. But when you use xtaskCreate pin to core, you're giving a direct order. You're saying, this task right here must only ever run on this specific core. This gives us the control we've been looking for.
So when should you actually pin a task? Here's a great little cheat sheet. The Wi-Fi and Bluetooth stuff, it's already pinned to core 0 by default, so just leave it alone, let it do its thing. Your own really time-sensitive code, like reading from a sensor or doing heavy math, pin that to core 1 to guarantee it has the CPU all to itself when it needs it. And for everything else, less critical stuff like logging data or updating a display, just leave them unpinned. Let the scheduler do its job and balance the load. The golden rule is don't overpin.
Now, what about getting tasks on different cores to talk to each other? You might be tempted to use a global variable and then protect it with something called a mutex, which is kind of like a talking stick that only one task can hold at a time. And yeah, that can work, but it's often slow and gets complicated fast. A much better, safer, and more efficient way is to use the tools that FreeRTOS already gives us, like queues. And this right here, this illustrates a really powerful design pattern. Just imagine you have a networking task pinned to core 0, and it receives some data. Instead of trying to process that data right then and there and potentially blocking the Wi-Fi stack, it just drops the data into a queue. Meanwhile, over on core 1, you've got a dedicated compute task just waiting. It pulls the data from the queue and does all the heavy lifting. This pipeline approach keeps both cores busy and your whole system way more responsive.
All right, so we've busted the myths, we understand the real model, and we've learned about the tools. Let's wrap this all up into a new SMP mindset that you can take with you to your very next project.
Here are the 5 big rules of thumb. First, don't be afraid of task migration. Expect it to happen and design your code knowing it will. Second, only pin a task when you have a really good reason, like super low latency requirements. Third, always choose SMP-safe tools, like queues, over trying to manage shared memory yourself. Fourth, remember that core 0 is the Wi-Fi core. Respect its workload and don't bog it down. And finally, and this is a big one, always measure your actual CPU usage before you go trying to optimize things. And that's really the final thought I want to leave you with. You might have spent a lot of time unknowingly fighting against the very nature of the ESP32. But if you can embrace this new mindset, if you can learn to design with symmetric multiprocessing instead of against it, the ESP32 completely transforms from a source of frustrating bugs into an incredibly powerful and capable real-time platform. And that, right there, is the ESP32's dual-core secret.